Professor Subir Sachdeb will be giving the lecture on entangled phases of quantum matter.
Okay, thanks, Rajdeep. Okay, so I'm going to talk about some basic background and then also try to end up by the end of my third lecture on relatively recent work, all associated with physics of the kind of models that Kedar introduced in the previous lecture, electrons with strong interactions in 2 dimensions. So please interrupt at any point. I'm going to use slides to begin with just to actually show you some experimental data, but mostly I'm going to work on the blackboards and go back and forth a little bit when I forget. When I get something wrong, I may have to consult my slides. Okay. All right, so just to give a general background, we're, one of the reasons for interest for systems of electrons, something wrong with the system, going in and out. Is it working? Okay. Are the cuprate high temperature superconductors. And these consist of these complicated compounds like yttrium, barium, copper oxide. But fortunately, from years of experiments and also first principle studies, we know that essentially all of the physics is controlled by a single layer of copper and oxygen, which is shown here. And these layers just stack on top of each other and mostly don't know anything, mostly are decoupled. At least for everything I'm going to talk about, I'm going to assume they're decoupled. So you have this 2-dimensional electron system and the important orbitals are a certain d orbital on the copper side and a p orbital on the oxygen side. But actually, you can even make a further approximation because the p orbitals on the oxygen sides are both filled. There's 2 electrons in that orbital. So you can also forget about the oxygen. So you're just left with a square lattice with 1 electron, with 1 orbital on each side. And what we're interested in is understanding how the ground state of the system evolves as you change the density of electrons on that side. So I'm going to call that density P. And P equals 0 is the case we have 1 electron on every side. So P equals 0, not the empty state. It's 1 electron for every side. All right, so here's the phase diagram, which has evolved over, at this point, nearly 30 years of experimental work. And you would wonder, why is it's so difficult to determine the electronic phase diagram of one material? Well, these materials are not easy to make. People have developed new tools from photoemission, Scannington microscopy, X-ray scattering, neutron scattering. Each one of these tools have advanced tremendously over the last 25 years. So now we know things to a great deal of precision. They're also very important have been studies in high magnetic fields. New labs have been built all over the world to study these compounds at fields as high as 100 Tesla, which are really the highest field anywhere on Earth, except the nuclear explosions or something. But on the electronic scales, these fields are also relatively small compared to the magnetic fields that electrons might experience from each other. Anyway, so I'm not going to obviously tell you about this alphabet soup of phases and what every one of these means. I just want to give a general picture and just point out a few important highlights and then turn to simple model systems which we'll try to understand. So first of all, at P equals 0, this is the case where you have 1 electron per site. Oops, sorry. Okay, I'll come back to that. You have this antiferromagnet. Now this is what I'm going to describe today. So this is 1 electron on every side. I'm only showing the copper sites. And these electrons arrange themselves in this checkerboard pattern, half of them up and the other half down. And this holds up to some relatively high temperature. For them to order in this way at finite temperature requires you to worry about the coupling between the layers so that the system eventually becomes 3-dimensional, but again, I'm just going to ignore that. All right, So that's one phase, and this phase is an insulator. And I'll discuss, that's what I'm going to discuss today. Why is it an insulator? And what are different ways of thinking about it as an insulator? In fact, Kedar's lecture is one way, might as well say. So we're going to use exactly the same Hubbard model that Kedar talked about. And he showed you could make this canonical transformation to a Heisenberg spin exchange model. And there he was just focusing on the spin degrees of freedom. He just assumed the charge doesn't fluctuate at all. So if the charge doesn't fluctuate, well, okay, then that must be an insulator. He drew these, n equals 0, n equals 1. So to create any motion, you have to put an electron in the n equals 1 level, which he was just ignoring. He's projecting it out. And so there's a gap. There's an energy gap to having electrical transport. And it's something that Kedar described using what's called the Mott point of view, the large U point of view. He was doing an expansion in 1 over U. There's a different way of thinking about it, which is the band structure point of view, and that's what I'm going to start with. And the reason I want to start with the band structure point of view because ultimately, we're not that interested in P equals 0. This is all, well, it's interesting physics, but at least in the cuprates, there's really very little mystery left about what's happening down here. Where all the mysteries are is when you change P so this is P equals 0. And as the previous slide showed, the reason for the excitement is that you have a superconductor. And that's something I'm going to say something about today. And with critical temperatures of order 100 Kelvin. So that's why those are still records among any compounds known today. Well, there's hydrogen and hydrogen sulfide under very high pressure, but that's probably not a superconductor of this type anyway. These are just ambient pressure. I could have done a lecture demonstration here showing you the superconductivity. Literally a tabletop experiment to see this. Okay, so there's the DSC, there's the AF, and then what else? So now what we're going to do when we turn on P is remove some electrons. So P is what's called the density of holes. So here's the antiferromagnet, 1 electron per site, and I remove a density P of them. So here I have 6 times 5, 30 sites. I've removed 4, so that's 4 over 30. P is 4 over 30 for this state. So that's the density of these vacancies or holes. Okay. So suppose I gave you this system and said, here's your system. The electrons don't interact with each other. Assume the electrons don't interact. They're free. And this is the density of electrons. What will they do? Well, what they will do is form a metal, because free electrons just occupy a band, and then there's a band with the Fermi surface. I'll go over this soon. And that Fermi surface has some size, and that size is determined by the density of particles. Well, that's called the Luttinger theorem. So in this case, it's easy. The question to ask is, what is the density of particles? Well, the first thought in your mind would be the density is P, but that's wrong, because that's a density relative to the antiferromagnet. So a conventional band theorist, going back to conventional solid-state physics, doesn't measure density relative to a half-filled band. They measure density relative to an empty band, if they're talking about electrons, or a filled band, completely filled band, if they're talking about holes. So for various reasons, it's better to think in terms of holes in the system. So what is the filled band? Well, the filled band is that's 2 electrons per site. So the density of holes in this state relative to this state is not P, it's 1 plus P. Okay, so there's 1 plus P holes because there's 1 hole on every site because you have 2 electrons. And on these sides, there's really 2 holes. So the total density, we just work it out, is 1 plus P. So a band theorist would say this should form a Fermi surface whose area is equal to 1 plus P. I'll go over that very quickly on the board soon. And indeed, that's what's, okay, I already said that. And that's what's seen in this region, FL. Okay. So there you can measure, you can do photo emission experiments and measure the surface, and the area here is exactly 1 plus P. All right, so that's again something we understand very well because free electrons, everybody understands that. Here we had immobile electrons. They form an antiferromagnet, and we understand that fairly well. And the name of the game is, how do you go between them? That's really what we want to understand, and you get superconductivity, and you get this pseudo gap, and you get this density wave. Well, I'll eventually say something about this by the end of my second lecture, and also strange metal. So, it's taken 25 years to characterize all of these, and the game still continues. In today's lecture, all I'm going to do is give you a very simple model of how you go from an antiferromagnet to a Fermi liquid. How do you go from a state where, as you change the density, you go from an insulator, which is an antiferromagnet, to a metal, which looks like free electrons. Okay? And there is a very simple theory that does that. It even existed before the discovery of these materials. You could call it the Slater theory of antiferromagnetism. It has one quantum phase transition, which is now often called the Hertz transition, and we'll say a bit about what happens. So, and we'll discover when we do that, it has some nice features, but it really doesn't look like the experiments at all, at least on the whole doped cuprates. But since the discovery of these cuprates, many other compounds have been discovered, these pnictides and electron-doped cuprates and other compounds. And it turns out that standard theory, on the whole, does pretty well in all those compounds. So that's will be the purpose of my lectures. Let's talk about this very simple standard theory of how you go between an antiferromagnet and a Fermi liquid or a free electron metal. What is it that you get? And then how are we going to put in the Mott physics that Kedar talked about? And will that Mott physics give us some of the new complications that are present in this phase diagram? Yeah, so this PG is the pseudo gap metal, and that's not something I'll say anything about today, so we'll come back to that tomorrow. Okay, so are there any questions then? So that's kind of the, the goal, which has been many people's dream for the past 20 years, is to understand these high temperature superconductors. So we theorists can keep thinking about all kinds of fancy ideas, and this list of fancy ideas is endless. But ultimately, we haven't known what the answer is that clearly until relatively recent. In fact, these experiments here are less than a year old. So that's turning out, in my opinion, to be one of the best clues to what's going on, as I hope to convince you when I get to talk about these things. So any questions? Okay. All right, so now I'll go to the board and just talk about metals and antiferromagnets in a very simple mean field point of view and try to correct the mean field theory and see what we get. Okay. I have some of this on the slides. This is from earlier lecture. I've given these lectures at various other schools before, and but let me do it on the board. Okay, so this is the model we're going to talk about, which is exactly what Kedar began with. So H is equal to minus some Tij. Plus U, someone I, and I up, and I down. Okay, there's a chemical potential and other things that I won't, inessential things that I won't write down. All right, so let's just begin by what I already told you works at large P, which is free electrons. So with free electrons, let's So at u equals 0, well, the electrons are just free. You have to determine the band structure. So Ek will be something like, minus 2T1 cosine Kx plus cosine Ky minus 4T2 cosine Kx cosine Ky, I think. So this is your square lattice. This is T1. This is T2. I want to make sure I don't make an error, so I did minus 2T2 cosine Kx plus Ky. And so on. And T3, okay. So you can now plot this band structure as a function of T1, T2, and T3. And the values of these numbers are very, very well known from photo emission experiments, STM experiments. We know exactly what these numbers are. And so you will get some, as a function of momentum, I'm only drawing one of the momenta, you get some dispersion like this. And then you fill up the lowest energy states, and then you have these Fermi points. Okay. But what we want to do is look at these points in 2 dimensions. So as a function of Kx and Ky, these numbers work out that the Fermi point, so this is the Fermi surface, look something like this. So this is 0, 0 here. So these are the occupied states. So electrons occupied. And this is minus pi to pi. So how many electrons do we have? What is the density of electrons? Well, it'll be D2K. So let's call this region here, this region A. So this is the region A. So you just integrate over this region. Say it has area A. You got to put a factor of 2 for spin. And that's the total density of electrons. And that's going to equal, well, the density of electrons, as I just showed you, is 1 minus P. That was the picture over there with 1 electron missing. So this should be 1 minus P. This is electrons. Or in terms of the area, so this is just area over 2 pi squared is equal to 1 minus P. So I'm going to often forget this factor of 2 pi squared. We just say the area is 1 minus P. What I really mean is area over 2 pi squared. Okay. Yes? Right. Yes. No, I'm talking about the renormalized value. So what I mean is you actually measure the Fermi surface in the actual system, and you fit the shape of the surface, for example. You fit the shape of the excited states from photo emission dispersion, and that's how you get the value of T1 and T2. Right. So when you look up the numbers, they're talking about experimentally observed, fully renormalized. Absolutely, yes, you're right. So that's kind of implicit in the discussion. Okay, so this is what it looks like, and now why is it that I prefer to talk in terms of holes? So these are the occupied states, and these are the empty states. Well, why do we want to talk in terms of the empty states as opposed to the occupied states? Well, that's because if I think in terms of the empty states and I center myself at this point, and this is pi pi, then rather than getting this very complicated Fermi surface, I just get a thing that's almost a circle. So this is pi pi. There's a circle here. You can move this over by 2 pi without changing anything. So now these are the occupied states. Okay. Right. Okay. So this, let's call that A prime here. This A is the better thing. So that's A prime, and let's call this A. So what's the area A here? So now the density of holes, if I apply the Luttinger theorem to holes, that should equal, that we know is 1 plus P. And by the same rule, that will be A over 2 pi squared. Okay. So these are equivalent points of view. And now there's a trivial identity, which if I've done my algebra right, it tells me that A plus A prime is 4 pi squared, which is the area of the whole square, which is exactly right. 2 pi times 2 pi is 4 pi squared. Okay. All right, so you can, depending on what day it is, you can work with this, or you can work with this. Now, we invariably prefer to work with this. And you can see why. It's just a circle. It's much easier to think about circles than these complicated shapes. But more practically, how do you measure size of the Fermi surface? I showed you the photoemission data, which is a very complicated experiment. But a much simpler experiment is the Hall effect. You all know, hopefully from your solid state physics, that the Hall resistance is 1 over some density times E, where E is the charge of the carriers. So because of this, this applies to some free quadratic dispersion electrons. That's how you derive it in your solid state physics class. And that derivation clearly will apply better here than here. So this system has a certain Hall coefficient. If I gave you these two pictures, and I asked you, is the Hall coefficient negative or is it positive? Well, clearly this is better thought of as a quadratic dispersion. So you would say positive, right? Hall coefficient should be positive. And what should it be? Its value. So it's positive, and the density is 1 plus P. So the Hall coefficient should be E times 1 plus P. Now, of course, you can get that Hall coefficient by starting with this picture. It's just a much more complicated calculation at that point. There's only one value for the Hall coefficient because this is the same system. And the correct value is this one. And that's why we could just going to use this language. Well, anyway. Okay, so that's free electrons. So now we want to include interactions. And I'm going to include interaction in really the simplest possible way by doing mean field theory. So we're going to U not equal to 0. And we'll do mean field theory. And that means I'm just going to replace U sum on I, Ni up, Ni down, by U sum on I, Ni up, times average value of Ni down, plus Ni down, times average value of Ni up. So this is, the usual mean field thing. Everybody sees the average of everybody else. So I just do that here. And then in terms of comparing energies, you want to take an operator so that its average value in whatever state you get is the same as the average value of the original operator. If you take the average value of the full energy here, it's average of Ni up times average of Ni down. But if you do that here, you get it twice. So you got to subtract out this thing to get the energy right. All right, so now there's a standard task before you. So let's call this H0 here. Okay, so that's H0. And this particular term with this average value, I'll call, I don't know, let's call it HU mean field. Okay. So now I have a Hamiltonian, And just to emphasize, this Hamiltonian depends on a set of numbers, which are the average value of NI up. So these are just numbers. We don't know what they are, but given the values of these numbers, I have a very simple Hamiltonian, which I can certainly work with, which is H0 plus 8U mean field. And this one also depends on the same set of numbers, Ni sigma, both up and down. So now the prescription is the following. We're going to, in mean field theory, just replace the original Hamiltonian by this Hamiltonian, where these things are just a set of numbers. And the way we're going to determine these numbers is by treating them as variational parameters. And we're just going to optimize the energy so that the energy of this Hamiltonian is low as possible. And that will be the best Hartree-Fock solution for this model. There's another way to say that, is that if you look at the minimization condition, which will be D expectation value of H, let's call this H mean field, over D n I sigma. So this must be 0 at the minimum. This turns out to be simply the condition that the average value of, well, how should I say, take the operator Ni, Ni sigma, so this is the operator, take its average value in the mean field ground state, and that should equal the number Ni sigma. Okay. So this, okay, maybe I'm being a bit sloppy here, but I presume you've all done some mean field calculation in your life. If not, slow me down a bit. So what I mean by this is that I have this Hamiltonian, mean field Hamiltonian, which is purely quadratic. So that Hamiltonian I can diagonalize and determine the expectation value of Ni up or Ni down. And that expectation value should equal the number that I put in here. Okay, so the way you do this is you pick some random number for these. And then once you've picked a number for these these expectation values, you actually compute the expectation value. And then you demand self-consistency. And that self-consistency loop is equivalent to the variational requirement that this mean field Hamiltonian have the lowest possible energy. All right? So that's a standard mechanical calculation that well, maybe in the tutorial you'll test my knowledge by asking me to actually do it. I'm not sure I can. But when the dust settles, well, actually, the true answer for this calculation can be quite complicated, especially at general P. And I think people are still debating as to what the best answer may be in some regimes. The reason being that you have an infinite number of variational parameters, because the dependence on I and sigma can be anything you want. So there's infinite number of parameters. Generally look for solutions that break translational symmetry in some simple way. And I don't know if people have even bothered to really determine what the global solution is. Maybe some people have, I'm not sure of the reference. But for our purposes, I'm just going to take a very simple solution, which we know works at very small p anyway, and then try to understand its properties. So we assume an antiferromagnetic solution, meaning that Ni up is some order parameter, I'll call it M0, times -1 to the Ix plus Iy, and sorry, Ni expectation value, Ni down is M0 times -1 to the Ix plus Iy with a minus sign. Did I get that right? Sorry, no. Yeah. So, right. So this is not right. Yeah, so put a half here, and then plus, thank you, 1 minus p over 2. So that's the density of electrons, 1 minus p. And so the up electron should, on average, have density 1/2. The down should have density 1/2 of 1 minus p. And then you allow them to be different in a staggered way. On one sublattice, there's more up electrons. And on the other sublattice, there's more down electrons. So on the even sublattice, when this is even, there's more up electrons. When this is odd, there's more down electrons. And that's really the mean field solution corresponding to the simple picture. Where's my note? So this picture here is, well, p is equal to 0, and m0 is equal to 1. Because then on one sublattice, I get n up equals 1, and on the other sublattice, I get n down equals 1. But generally, these m0 and n, m0 can be anything you want, and you want to choose the m0, which minimizes your energy. So now you just minimize with respect to m0. So I've reduced, by this ansatz, I've reduced an infinite number of variational parameters to just 1. Because I know it works at p small, and let's assume it works at p non, just to keep life simple. So we just want to understand what happens to the system as I vary the value of m naught, okay? So what you will find typically when you solve these equations, not at half filling, but at generic filling, you can plot the value of m0 as a function of, say, u over t. So there'll be some critical value, u critical, where it certainly turns on and then becomes non-zero. So here, at very small u, you just have a metal, a usual Fermi liquid. And out here, you have an antiferromagnetic metal. Now, if you do this at exactly p, this is for p not equal to 0. If you do it for exactly p equals 0, it turns out u critical is 0. Well, no, this is fine. If you just had what's called a nested Fermi surface, which in fact you don't here with the T1 and T2, with the T2s. So actually, this is fine for any p. So what I want to do in the remaining part of the lecture is, first of all, understand the nature of this metal. What does this look like? Is this always a metal? Or is there something different here? Yeah, let's assume p is not 0. Because some strange things happen here when p is 0, which we want to discuss. And then say something about, what's happening near this phase transition. And if I time things right, what we'll see by the end of the lecture is right near this critical point, you get D-wave superconductivity. And that was actually known even before the discovery of high TC superconductivity. So that's very encouraging. It means you're on the right track, because that's what the experiments see is D-wave superconductivity. There are many other details that don't work out, but let's just start with this theory. Okay. All right, so let's first discuss that you have such a mean field solution. What is the nature of this metal? What does it look like? And what do I mean by that? Well, anybody studying metals, the first thing you want to know about a metal, if somebody tells you have a metal, is what is the Fermi surface? Where are your quasi-particles? What is the nature of the Fermi surface? What is the Hall coefficient? And then you can compute other things. So what is the nature of the Fermi surface then when you have m0 not equal to 0? Okay, so now let's go back. We're going to start with the same Hamiltonian, and we're going to assume that I'm in an antiferromagnetic state. So I'm just going to replace this by by that expression over there. And apart from various constant, the important thing that you're going to get, and I hope I get the factors of 2 correct, we get m0 times sum on I of minus 1 to the ix plus iy times c dagger I up, ci up minus c dagger I down, ci down. So that's my effective Hamiltonian within the antiferromagnetic state. I have band dispersing electrons, and then I have this term which is up on one sublattice and down on the other, and staggered. It doesn't have the full symmetry of the square lattice. Okay? All right, so now naturally what you want to do is take a Fourier transform. And for a Fourier transform, it's useful to know that I can write this as e to the I k dot r. K is pi pi. So that's the so-called antiferromagnetic wave vector. So you have antiferromagnetism at the wave vector pi pi. And so now I can just take a Fourier transform of the whole thing. And so this will be the dispersion which I erased. Sum on k, epsilon k, times c dagger k up, c k up, plus c dagger k down, c k down. And now if I take the Fourier transform of this, what you're going to see is that normally if you didn't have this factor, then the momentum here will be the same as the momentum there after a Fourier transform. Here, because of this factor, the momentum has to differ by exactly this momentum, which is k, which is pi pi. So you're going to get a term which looks up to factors of 2 times m0 times c dagger k plus k, c up, ck up, minus c dagger k plus k down, ck down. Okay, and then the chemical potential. Okay, so this term is not diagonal in momentum. It changes momentum. So you can think of this as Bragg scattering. You have some potential due to the antiferromagnetism. The potential is at wave vector pi pi, and the electrons come in and Bragg scatter off that potential. Now I have to diagonalize this. So this is the second easiest Hamiltonian to diagonalize because it's a 2 by 2 matrix. And it's a 2 by 2 matrix because twice k is equal to 0 up to reciprocal lattice vector. So I can write this Hamiltonian okay, is this a question of how I define? Yeah, I guess I did put a u over there. Yes, thank you. So there may be a factor of 1/2 also, but I won't worry about it. So this I can write in the following way. Okay, easier way to do this is to go put this magnetism in the x direction. But all right, at this level, this is fine. Let's put it in the z direction. It gets a little bit tricky with the z direction because then you have to sum over half the Brillouin zone. But anyway, so I can write this as sum on k with a prime because I'm only going to sum over half the Brillouin zone, meaning here's my Brillouin zone. I'm going to take half of it. This is called the antiferromagnetic Brillouin zone. And the prime means I'm summing over this guy. So this is the prime. So if I take any point inside this Brillouin zone and I move it by capital K, so if I pick a point here, which is K, and I move it by capital K, it'll be some point over here. So if I start here and I add K, I get something in the second Brillouin zone. If I add another K, I come back to this point. Well, I really come back to this point in the next Brillouin zone, but that's 2 pi, so it's really the same point. Okay? So k plus 2k, in other words, k plus 2k, this is a useful thing, is equivalent to just k. Because then it's 2 pi. 2 pi is the same as nothing in a lattice. So basically, this point is coupled to that point, and that's it. And that point is coupled to this one, and they go back and forth. That's why you get a 2 by 2 matrix. So then, and you have to sum over only half of them, because if you summed over the whole Brillouin zone, you're double counting. So that's why the prime, and you'll get C dagger k up, C dagger k plus k up, and the matrix ck up, ck plus k up, and then a similar thing for down. Now, there's one advantage of putting the spins in the x direction. If you put them in the x direction, both sums, you get rid of both of these things. You get rid of the prime and you get rid of the two sums. But okay, it's fine at this level. If you're trying to do a more sophisticated calculation of anything, that's a better way to proceed. So plus up goes to down with a minus sign. All right, so what do you have here? You have ek plus k, and um0, um0. Your m0 goes to minus m0. All right, so now we can easily diagonalize this, and this gives me the dispersion ek is equal to ek plus k over 2 plus or minus square root of okay. So that's my answer for the dispersion, and this is the dispersion is over the antiferromagnetic Brillouin zone. So now what's happened is previously I had just one band. Now I have two bands because of the plus and minus, but I have only half the Brillouin zone to play with. So sometimes I'm conserving the number of states. So I have two bands here, and I have 1 minus p electrons. I just got to fill them up, see what I get. Okay. So you can give this problem to Mathematica, it'll generate lots of plots. It's a complicated thing to do, but after a while you get, you kind of learn ways to understand how this all works, and I'm going to just qualitatively sketch how you think about it. But of course, the real calculation is what I've shown on the board. So how does one think about what happens, what does the band structure in the Fermi surface do when you play this game? Okay, so this is kind of how one way to proceed. Okay, so let's say we start out with some band structure that looks like this. I need some colored chalk. Okay. So that's my original band structure. And what we see from here is that this band structure, that's the whole band, but okay. This band is mixing with the same band shifted by capital K. So the Fermi surface, the line of zero energy states, is also shifted by pi pi. So this is kx, this is ky. And this thing shifted by pi pi would be a circle over here, which I can redraw as the original Fermi surface. So it's this line. Okay. So this is Ek equals 0. Well, okay, let's do it the other way. Since we're talking about electrons, this is Ek equals 0, and this line is Ek plus K equals 0. So this thing, if I look at this matrix, one of those lines is where this vanishes, and the other point is where this vanishes. Now, when is the off-diagonal term the most damaging? The off-diagonal term is the most damaging when both are 0. So there's a special set of points where the diagonal elements in that matrix are all 0, and these are these points, where these 8 points where they intersect. So at the points where they intersect, I have one band with 0 eigenvalue, I have another band with 0 eigenvalue, but at those points, they also mix with each other. So in fact, they no longer have a 0 eigenvalue, meaning you open up a gap. So these are the points where there's no longer going to be a Fermi surface once m naught is not 0. Okay? So what is going to happen is you're going to open up a gap, and so let's open up a gap, get some level repulsion over here, and then let's imagine that everywhere else, not much changes. And the reason not much will change everywhere else, because on the other regions, this is 0, but that's not 0. And then in that case, the off-diagonal elements may not matter that much, because as long as this is bigger than that, the one that's non-zero. So if this is non-zero and it's bigger than this, the off-diagonal matrix element doesn't do much. So everywhere else, the Fermi surface doesn't move very much. Right where both of them vanish is where it moves the most. There's got to be a gap there. Okay, so therefore, what the Fermi surface will look like is something like this. You're going to get a little piece here. And okay, this is a very bad figure. You get a little circle over here. Okay. Anyway, they're all the same size, but forgive me. So these are called, so this is a pocket. And that's also a pocket. The colors are not visible. Okay, maybe I'll try yellow. Give me a chance to draw the figure better. Let me draw it better. And bigger. Okay. It's better to draw this guy first. All right, so then there's this guy. So these are the parent Fermi surfaces. Okay. And then after, so this is for m equals 0, this Fermi surface and its image. And then you open gap at these hotspots, as they're called, and you get a Fermi surface that looks like this. Of course, this is just the opposite side of that. So there's a little pocket here. This is the opposite side of that. This is a pocket here. And then there's 4 pockets here. So the Fermi surface, as we say, the jargon is reconstructs. So m naught not equal to 0 implies Fermi surface reconstructs. Okay. Now the total number of electrons still is 1 minus p. But remember, there's 2 bands everywhere. And so it's a bit complicated. So what this means is that at least one of the bands is crossing 0, but the other one is not. And then it's a question of, is the other one that's not above the Fermi level or below the Fermi level? So that involves, doing some, it's just very tedious mathematics. You can just take those formula, play with mathematics, and look at all the bands. And it's rather complicated. But what you then find is you should think of this as a whole pocket, and this is an electron pocket, because the second band over here is above, and there over here it's below, and there it's above. So anyway, what this means is that these states, if I look at this Fermi space, these are occupied states. So this is an electron pocket. And this turns out to be empty, and that's a whole pocket. what that means is that inside this region, there are, inside the pocket, there's one band that's full and one band that's empty. Here in the inside region, both bands are full. And outside, only one band is full. Okay, so here there's two bands full. Here there's, everywhere else there's one band full. And in this region, there's 0 bands full. Because you've got two bands floating around. And really, I should be drawing the Diamond-Brillouin zone to figure all this out. But there's no reason why you should know all of this. It's because you just have Mathematica to figure all this out. But I need this information to say something about the size of the Fermi surface. So, we have this general relationship that in any Fermi liquid, the size of the Fermi surface is related to the area over 4 pi squared. So what happens here is that the area of the electron pocket, this region, electron pocket, minus the area of the whole pocket, turns out to divided by 1 over 2 pi squared, turns out to equal P, minus P, because the density of electrons is, and here we are measuring electron pockets as having positive area and hole pockets as having negative area, as is clear from this sign. So if we just work that out, just counting states in this horribly complicated geometry, this is what you get. Okay. So what happens, so this is for small m0. And now you keep increasing m0, and then you can ask what happens. Let me look at the special case where p is equal to 0. So if I look at the case p equals 0, and m0 large enough, so what you see is, as I increase m0, the difference of the area of the electron pocket and the whole pocket is preserved, because the density of electrons is preserved. So basically, as you increase m0, they'll trade off with each other. If one becomes smaller, the other has to become bigger. Sorry. If the difference is one becomes smaller, the other one has to become smaller too, because the difference is constant. So now p equals 0 is a special case where the areas are equal. So if I keep increasing m0, the gap here becomes larger and larger. And as it becomes larger and larger, this may shrink, but this has to shrink an equal amount. And you could reach a point where they're both 0. That's an allowed solution. On the other hand, if p is not 0, so p is, say, positive, then the electron pocket can shrink to 0. The whole pocket cannot disappear. It has to stay there. Otherwise, you can't satisfy this equation. So what this tells us is that something very special about p equals 0. At p equals 0, the Fermi surfaces can disappear. But at p not 0, there's always a Fermi surface. So at p equals 0, you can get an insulator. So m0 large enough, we obtain an insulator with a electron equals a hole equals 0. Okay. So that's what I began the discussion with. I said this is an insulator, and it was obvious from the way Kedar talked about it. Here, it took us much more work, paradoxically, because we started from a small u, perturbation theory. So that insulator is basically this insulator, that stayed right there, where from Kedar's point of view, it was obvious it was an insulator, but now we have finally succeeded in in getting an insulator. So at P equals 0, this picture is not quite right. Eventually, M0, so this is P not equal to 0. If I did this for P equals 0, well, M0 can keep increasing up to some value. At some point, this is an antiferromagnetic insulator. And if P is not equal to 0, well, then one of the hole or the electron pockets must survive. So I think I have some pictures of this on the slides. Yes? Yeah. No, yes you do, yes you do. So if T2 is 0, then let's see, if T2 is 0, then you immediately become, okay, so when T2 is 0, this UC goes to 0, but you'll still have the pockets for a while. And eventually you'll get, oh, if the band is really flat, yeah, then both of these regions disappear. Okay, but if T2 is not 0, then it looks like this. So let's see. Okay, so here's some pictures. Those are the two pictures I began with, the areas, and then, oops. So here's, now you start with the Fermi surface, you translate it by pi, then you open up at those hot spots where you have diagonal zero matrix elements, and then you get these electron pockets and hole pockets, where here I'm calling it phi, not M0, sorry about that. And then as you increase M0, this is the original state, this is a generic P, you open up electron and hole pockets, and if you keep doing it further, you only have the hole if your P is positive. So then this goes to 0, P is positive, and this equals that. So this is the evolution. And for the special case P is 0, the area of this is equal to the area of that, and they both disappear. So all of these pictures, these very complicated looking pictures, they're simply coming from plotting this function and filling the lowest energy state. That's all I'm doing, is plot these two functions and fill the low energy states. And there's all these very important conservation laws on how these Fermi surfaces must evolve. Okay, so then, this line is where there's a quantum phase transition, which is this UC over here. And we want to, next step is think about this a bit more. Okay. But the insulator will be important. So this insulator, is an insulator where we have gotten around the Luttinger theorem on the volume of the Fermi surface by a very special route. So the Luttinger theorem says that if you have a density of 1 electron per site, you must have a Fermi surface that has size 1. So you would say, okay, let me just crank up U. That's a weak coupling statement. The Luttinger theorem is expected to be always whole. So no matter how strong the interactions, you're going to get a Fermi surface of size 1, even at P equals 0. So we've gotten around that, and the reason we've got around it is because you've doubled the unit cell. You've broken a symmetry. You have 2 sites per unit cell. And in the doubled unit cell, density of electron 1 is equivalent to completely filled band. That's what happens when P is 0. I have 2 bands. So in this Brillouin zone, I had 1 band going everywhere. But when I broke it up this way, I have 2 bands here. And each band has density 1. Whereas previously, the full band had density 2. So 2 electrons per site. But now, since I have half a Brillouin zone, 1 band has density 1 and the other band has density 1. And if I manage to acquire a band gap, then I can get an insulator. So it's absolutely crucial here that there is a broken symmetry, that I've doubled the unit cell to allow me to evade the Luttinger theorem. So broken symmetry is doubling the unit cell, allows a solution with a band gap and no Fermi surface. And this is consistent with the Luttinger theorem. So that's the very important point here. That antiferromagnetic order allows you to get a result where you get an insulator where you didn't expect an insulator because the density of electrons was not even electrons per unit cell. That's what Bloch taught us. The only way you get an insulator, you have even number of electrons per unit cell. Here's a system with an odd number of electrons per unit cell. It still becomes an insulator. The reason is that the magnetism doubles the size of the unit cell. If you have 1 electron per the original unit cell, in the new unit cell you have 2 electrons. So you're back to satisfying the Bloch-Luttinger criterion for getting an insulator. There's still an even number of electrons now in the new unit cell, which has been doubled. So this seems to put a fundamental correlation between getting an insulator at density P equals 1 and having a broken symmetry. And in the experiments, antiferromagnetism is actually present, and so you'd say, okay, this theory is great. It works, consistent with that. Now, however, some of the much deeper understanding of these issues has emerged in the past 2 or 3 decades. And now we know there is other way to get an insulator without breaking a symmetry. So here, this type of insulator where the broken symmetry is crucial to getting insulating behavior with an odd number of electrons is called a Slater insulator. So we should call this a Slater insulator. And this was, Slater's point of view, that having insulating behavior with 1 electron per unit cell requires antiferromagnetism, because otherwise you can't be consistent with Luttinger's theorem. So what we understand today is that there's another route, and the other route is to have topological order. And you can get insulators, they break no symmetry, they don't have antiferromagnetic order, but they have topological order. And that's what I'm going to show you by the end of next lecture, how that works. And there are indications that at least for the whole-doped cuprates, it's very important to think about that kind of insulator. In other words, if this picture of the Slater insulator is correct, so I start with a Slater insulator, I dope it, and what I will show you, I don't know how I'm doing on time, half an hour left. I will show you get a D-wave superconductor. Everyone's delighted, you declare victory, and you go home. So who needs MOT? So that picture actually works very well for pnictides and many other compounds I'm not showing you. So it's very important and correct. But if you look at these whole-doped cuprates, there's just a lot more going on, especially this PG and all of that. And my thesis is that, and other people's also, but I think it's become especially clear in the last 2 or 3 years, that we really need to think about mod insulator, that this thing, it's more a mod insulator than a Slater insulator. It's obviously a Slater insulator because it has a broken symmetry here. But that broken symmetry is relatively weak and can be easily removed by just changing P up to 0.03, it's gone. But you still remember something about the mod aspect of it, which gives you all this fun stuff in between. All right. Okay, so that's a review of band theory for an antiferromagnet. Any questions? Correct. It's very schematic. I mean, large value of U over T, M naught, will become some universal value like 0.333 or something that you can figure out from. So if I really want to know what's going on out here, I have to do what Kedar did. I do the canonical transformation, get an antiferromagnet, do numerics on the antiferromagnet that Kedar showed you. You'll get the value of M naught here. Now, in his approach, that's all you learn about this insulator. You know nothing about this. This is a metal because the charge gap has gone to 0. Kedar's approach here, the charge gap is infinity. Here, the charge gap is 0 because you have opened up at this point. So if I draw the Fermi surfaces, in here, I have no Fermi surface. Here, I have electron and hole pockets of equal size. So these appear and they start to grow. Eventually they intersect, and finally, here I get this. Okay. So everything Kedar said is in this region where there's a complete gap to charge excitations. They're just the highest energy in the problem. It's practically infinite. And I'm reaching that now starting from u equals 0. Okay, but what was your question? Zero M naught. No, it's not. When M naught is, this is M naught. At this point is not an insulator. It's over here, right? So this is not a phase bond. So this is a plot of M0. This is the value of M0. This line, it's not a phase diagram. It's a value of M0. M0 is this axis. M0 is 0, and it becomes large. The only thing I'm varying is u over t. Okay, it's not a two-dimensional phase diagram. Sorry, it's just a plot of M0 versus u over t, and it's shown pictures of what the Fermi surface looks like. Okay, so that's because the Fermi surface has a rather non-generic shape in that case. If you have only nearest neighbor hopping and you're half filling, then the Fermi surface actually is, then the dispersion, then Ek is just minus 2t cosine kx, that's cosine ky. And now if you want to plot the locus of points, you plot the Fermi surface at Ek equals 0. That's at half filling, that turns out to be the condition. The locus of points where this is 0 happens to be this rather straight, this shape. It's not a smooth shape. It's a very special feature of this function that has got this diamond on which Ek is 0. So you have these very flat Fermi surfaces, but that's very singular. The moment you put on T2, all of this disappears, and you get a more generic behavior. Any other questions? Okay, so what I want to do now, and I think I'm going to use the slides because I have it already, is say something about this point. What would we do? What would you say the theory of that point? And then show you, so you have to go beyond mean field theory. So this is mean field, just Hartree-Fock. You want to look at fluctuations beyond Hartree-Fock and see what we get. And the beautiful thing is you get something that, is what was then subsequently seen in experiments. Okay, so I'm just going to use the slides if there's no objection. And I only have 20 minutes left, so. All right, so the way you can do fluctuations, so when you do the mean field theory, it has the virtue of being a variational approximation. It's something very well-defined, and you can be guaranteed, even though your mean field theory is stupid, your ground state energy is an upper bound of the ground state energy. So it's got some value. It's a variational estimate. Now I'm going to be much more cavalier. I'm not going to be so careful about trying to get the best ground state energy, but I'm going to set up a formalism that allows me to at least understand something about the structure of fluctuations and corrections beyond mean field theory. And those corrections are especially strong right near this quantum critical point. So the basic trick for much of this is something called the Hubbard-Stranovic transformation. And there's some arbitrariness in this transformation where you almost have to guess what the answer is going to be before knowing how to do it. So here, from all our hard work with mean field theory, we're satisfied we want to look for antiferromagnetism. We want to look for antiferromagnetism in a unirotationally invariant way, so that the fluctuations, remember that the original Hamiltonian was rotationally invariant. And this is how you do it. You take the Hubbard interaction, and you write it like this. So this is just an identity you can verify for the electron operators. And then you take SI squared on every site in the Feynman path integral, and you do this Hubbard-Strudanovic transformation by introducing this fair field Ji. So if I integrate over Ji, this is just a Gaussian integral, you'll get back this, which is this term over here. And the reason I'm doing this is because I'm interested. So average, you can see from this path integral that average value of J, which is the saddle point of this, is just the average value of S times some U factor. So J is a measure of my local spin fluctuations. So I want to introduce another degree of freedom. In addition to the electrons, I want to introduce another degree of freedom, which is my order parameter. I know there's a broken symmetry. I pick a direction in spin space and a particular orientation in space. And I want to have some degree of freedom which represents this broken symmetry. That's the Landau point of view. So I'm going to write down a Landau functional, which tells me about the antiferromagnetism. But at the same time, I don't want to forget the Fermi surface. I want to keep that around too. I mean, in conventional nets matter physics, we learn, there's two important reasons for having very low energy modes. One is you have broken symmetries, then you have these Goldstone modes or something. And the other is you have a Fermi surface with the special property of free electrons. And here you have both. So you have to really worry about how Landau Fermi liquid theory interplays with Landau's broken symmetries. Landau versus Landau, but we get something different. So what do we get? All right, so I just do this on every site. And now I have a path integral where I have the original electron variables and this new field J. So I have twice as complicated a path integral, but I'm not scared by that. And then furthermore, I assume that this is my order parameter. So this includes an arbitrary spatial dependence. But let's assume, a reasonable assumption is that the important spatial dependence is going to be antiferromagnetism. So at this wave vector capital K, which is pi pi, there. So I'm going to take Ji and write it as phi times this. So of course, I can always do this. It's just a definition. But now the point is this, I'm going to assume very slowly. So that's my Landau order parameter. It's going to vary slowly, and it's the envelope function of the local antiferromagnetic order. And it's a vector because the spin can point in any direction. Okay, so then this is the path integral. I have the integral over phi, I have the integral over the electrons. This is the electrons, the dispersion. Then I have this coupling between the order parameter phi and the electrons. That's precisely this term over here, this term here, except I've replaced this. Now m naught is no longer a constant. So this was m naught is a constant pointing in the z direction. But now I can imagine a more general situation where m naught varies from space to space and also has different orientations. So this term, in the more general form, looks like this. The coupling between my m naught, which I'm calling phi, and the two electrons. And phi is a spatial dependence. And this e to the ik dot r is precisely that factor. M naught comes inside. This is the z component only. So if I take phi just pointing in the z direction and constant, this becomes exactly that. Okay, so this is sometimes called a Yukawa coupling because it's sort of like, I don't know why I put this phi inside the c's. This is many years ago, anyway. And then I have some action for phi, this j squared term. And I just replace the j squared term by some Landau free energy for phi. These are fluctuations of the antiferromagnetic order parameter. So here, point of view is I have a Fermi surface as the one culprit for low energy modes. I have a broken symmetry for which I write down a Landau free energy, and then I just couple them together as expected by symmetry. That's the name of the game. People familiar here with Landau theory of phase transitions and mean field theory? Okay, but that's something we can discuss in tutorial if you're not. Okay, so now if I put phi equals constant, I basically reproduce all the stuff I showed you over there. Okay, yeah, phi equals constant. These are the band structure. I showed you that also. And then I showed you how the Fermi surface evolves. All looks great. So yeah, so this is it. Electron. Okay, I'm going to skip this. This is all kinds of Landau damping and all of that. Let's talk about this. Okay, I can come back to Landau damping later. Won't be that important for anything I'm going to talk about. All right, so now I have a theory. Let me go back to the theory. Yeah, so here's my theory. And I'm going to assume that I can just do perturbation theory in lambda. That's all I'm going to do, okay? And for phi, I'm going to ignore the phi to the fourth term. And S, I'm going to assume is very small. So when S is 0, then in Landau theory, I'm at the critical point. So that's this critical point you see over here. This point here is when S is 0, because on one side, phi is not 0. On the other side, here phi is 0, there phi is not 0. So what I have then is a theory that looks like this. I have electrons moving around in some band structure. Easier to see this in diagrams. So I have an electron. So that has energy Ek, or its Green's function would be something like omega minus Ek. So there's some propagator for the electron which has energy Ek. And I have this phonon, this phi field, which I represent like this. And at quadratic order, in fact, I'm going to just ignore this term. You don't even need this, but anyway. If I just take the gradients term and this term into account, this is something like 1 over k squared plus S. So there's some collective bosonic mode, which is just the antiferromagnetic order of the electrons themselves appearing and affecting the electrons. So the puzzling, so this is sort of analogous to the electrons and phonons. We know that in a solid you've got electrons moving around, you've got phonon vibrations, and they couple to each other easy, and then you do BCS superconductivity. So here, it's not as simple. The phi that I'm writing down came out of the electrons. So it's almost like double counting, but it isn't really. The phi is not some new independent degree of freedom like the ions moving. It's a collective property of the electron, sort of like a plasmon or some, it's an exciton really more precisely. It's a spin exciton, which is some collective mode. And we think that collective mode has an independent identity because we're near this critical point where we know this collective mode has to become important because it condenses and gives you the antiferromagnet. But other than the origin being a little more non-trivial, the structure of this is not so different from the electron phonon problem. And then we have this coupling, lambda, which we can write like this. So the electrons go by, and this is lambda and comes with the sigma times e to the I k dot r. So if you've studied the BCS theory, in the BCS theory of electrons coupled to phonons, you have some electron-phonon vortex, and then you have a propagator for a phonon. And pretty much you can think of the phonons as being off resonance, so you can put the omega squared term here if you want. Frequency. So really the whole thing looks very similar to the electron-phonon problem. And the natural thing to do is to turn the crank and find superconductivity, because BCS told us how to do it. They told us anytime you have an electron coupled to a boson, there's going to be some attractive interaction, and that attractive interaction would be, one electron coming by. BCS said it emits a phonon. Here it's going to emit this phi excitation, which is some kind of called a antiferro, I don't know what to call it, antiferromagnon. And then the second electron goes by, and it feels an attraction, and then they pair. Okay. All right, so we're done, right? So so I can just open up the book and do the calculation. It's not as simple, and really the reason it's not as simple is these factors are different. There's a factor of e to the I k dot r here, which means that this electron, if this electron is momentum k, that electron is momentum k plus k. That doesn't happen for the electron phonon system. And there's a factor of the spin. That's also different. So these are the two differences, the fact that it's at momentum capital K, not zero momentum or something, and there's a factor of spin, the Pauli matrix. It's precisely those two reasons is why the superconductivity you get is not S wave, but D wave. And you put that in, but otherwise turn the BCS crank. What this theory predicts is you get a spin singlet superconductivity that has a D waveform, or D-like. For some other Fermi surfaces, like in the pnictides, you get what's called S prime, which is in fact also what's observed for those materials. So that's what I want to show you, how that calculation works. So we forget all this. This is for the critical point. We'll come back to that. So in fact, this type of calculation was done in this remarkable paper in '86. Cuprate's high temperature superconductivity was discovered in '87. And they're talking about the three-dimensional Hubbard model. That was the only mistake they made. They should have talked about the two-dimensional Hubbard model. And the singlet dxy, singlet dx squared minus y squared is enhanced, which is the correct answer. Okay, so So we're going to sit here and look at exchange of phi excitations. And as I said, from this, if an electron is momentum k, the other electron here will have momentum k plus k. So it'll go from this point on the Fermi surface to that point. So I'm going to assume U is smaller than UC. I'm in the metallic phase over here, and look at the BCS instability. All right, so this is how it proceeds. So there's my coupling between phi, which I showed you over there. This V written out here is this graph. So if I can write this out in numbers, there's a factor of sigma here, another factor of sigma here. This is k plus k prime plus k. And this thing comes in as 1 over k squared plus s. So all of that, it gives you this thing. Yeah. So here, we put the capital K, we put the electrons without the capital K, which means that this little k has to be shifted by capital K. So instead of putting the capital K there, I put it inside over here. That's just a change of variables. Okay, so now once you write it this way, this is exactly the BCS form. Introduced to the BCS mean field theory. The only difference, as I've emphasized, is this factor and this. So for BCS, this wouldn't be there, and this wouldn't be there. But it's the same calculation. All right, so now you just do the BCS. It turns out you take a spin singlet pairing. Just do the pairing amplitude, and I can do this in the tutorial if you want, but this is completely standard BCS mean field theory applied to this Hamiltonian. This is the famous BCS gap equation. And now you see why it has to be D wave. That has to do with the fact there's this minus sign out front. So when you do this for BCS, this is a plus sign. The reason this is a minus sign out front is because of these sigmas. The sigmas conspire when you do this through you get a minus sign. So you're getting this minus sign, but you're also getting this capital K. So if you didn't have the minus sign, you didn't have the capital K, BCS said the solution is delta equals constant, which is S wave. Now you got to get rid of the minus sign. This means that when this is large, delta K should have the opposite sign from delta P, which means that when P minus K is approximately equal to kappa K, capital K, delta K should have the opposite sign, delta P, as I say over here. So let's look at this in pictures. So if I pick this point here, so these two are paired, then this will get this point here plus capital K is this point. So whatever the function delta is, delta of K, it should be positive here, it should be negative there. Only then will I get rid of this minus sign, and then I can find a solution. Okay. So it turns out the way to what the solution then, where you go? Yeah, so if this is positive, so red is positive, green is negative. So you want a solution where this Cooper pair, so here's a Cooper pair A and B. So that's, let me draw this picture here. We have a Cooper pair A and B. So so this Cooper pair comes along, and A scatters to C, and B scatters to D. So A goes to C, and B goes to D. And then the pairing amplitude, if it's positive here, has to be negative over there. And that's what happens. So red is positive and green is negative. So A goes to C and B goes to D. And they're both happy. Here they were positive. So this Cooper pair had positive amplitude. That Cooper pair has negative amplitude. So the simplest function around the Fermi surface that satisfies this criterion is this function, cosine kx minus cosine ky. Has precisely the property that is positive here and negative there. That's the D. So that's why it's D wave. You have to flip the sign as you scatter by pi pi around the Fermi surface. And it's intimately linked to both, as I've said many times, the fact that the wave vector is near pi pi, and it involves spin exchange. If you did this for charge density wave, this wouldn't work, because you wouldn't have the other minus sign. But it works for antiferromagnetism. They have some charge density wave instability at some finite k that's not going to give you spin singlet superconductivity. It might be some spin triplet, but if that turns out to be, at least we don't see too many examples of that in the real world, if any. But there's many examples now of high TC superconductors, moderately high, which all seem to be in this class. Okay, that's exactly the right time, so I'm done. Okay, questions? All right, well, yeah. Yeah. Correct, yeah. Yes, you would get coexistence of antiferromagnetism and superconductivity. So they don't have too much of a difficulty coexisting. So superconductivity has a hard time with ferromagnetism, but not with antiferromagnetism. Well, so this theory, the theory as I presented it so far, doesn't know about the Mott state. By Mott state, I'm assuming you mean a state which is an insulator without a broken symmetry. So this is a theory of Slater insulators. What I presented is a theory of dope Slater insulators, and despite its bad reputation, it's incredibly successful in many, many compounds, except possibly the one with the highest DC. But everything else, it seems to work very well.
Any other question? So one question. So
Yes.
push it towards the metallic side. And
Yeah.
presumably, if you move too far away from the critical point, you can't use this propagator for the
Sure.
influx. So what sets that scale, how far you can move out and still have this theory
Well, I mean,
well described?
so you don't really need S to be very small. I mean, even if you're very far away, there's an attraction. So you still have the BCS log. I mean, so like we know from BCS that infinitesimally small electron-phonon coupling always gives you TC. So, so ultimately, I turn this off. Right. So, okay, let me try. So the cuprates don't look like this, but let me draw a phase diagram from some other material. So there's material, this barium, iron, arsenide. It has a phase diagram, which looks much more like the theory I presented. So actually, I have some talks, but it'll take me. I'll show it to you in my next lecture. I certainly have some pictures like this. So you have some doping of some compound and temperature, and there are compounds where you have, in fact, this is spin density wave order, or antiferromagnet, the same thing. So people interchangeably call an antiferromagnetic metal as a spin density wave. Here, in fact, it's metal down to it all the way to x equals 0, and then you have what people draw as some deep superconductivity like this. So what I've shown you is that near this point x, which is what I drew, which is UC over there, you have superconductivity. And what Rajdeep was asking, well, what happens for large x? Well, really, the theory doesn't show anything like this. It just keeps going forever. Probably in real world it does, except maybe disorder and other things. Becomes immeasurably small.
At some point, retardation issues would come into picture.
Right.
And you have lots of low energy incoherent spectral weight for the spin fluctuation.
Right, but in the absence of any pair breaking, unless you have spin impurities, there's this, and the disorder is not so strong that you have localization.
Okay.
There is this Anderson theorem that DC is not zero. Yeah. Yeah. No, that wasn't any filling, it doesn't matter. To get an insulator, you have to be half filling. To get an insulator, you have to be half filling, but for a generic P, the only thing that changes is at very high U, you don't get an insulator. Theory doesn't care about it. So, in other words, I'm sorry, I thought through this crucial phase diagram. Let me redraw it over here. So that theory I was showing you as a function of U over T, I was plotting M naught. And there was some critical value of U, after which M naught went up. And then, so this is basically the phase diagram at P not equal to 0. And it's a metal everywhere. AF metal or an STW, and this is just an ordinary metal. Now, if you exact at P equals 0, the only thing that happens is you get an insulator here at P equals 0. At any non-zero P, it remains a metal forever. But I don't really care about that because I'm really interested in what happens here, which is this point here. So that region here for large U at P equals 0 is this region here. And in the pnictides, in fact, it's not even an insulator, even at U equals 0, P equals 0, because U is presumably not large enough. So the pnictides, even at P equals 0, seem to be here, where the cuprates are here at P equals 0. But none of that matters for what's happening here.
Any other questions? Okay, so let's thank Subir.
Okay.
But
So
before
next
you...
time at least my insults that I'll talk about mod insulators next time. I'll show you how this can be modified to how you can get around Luttinger's theorem by topological order and gauge theories and lots of